now let's take a bit of time to look at TCP. So what is TCP? We've been talking about how we provide reliability. TCP is a level 4 protocol responsible for transport. And it provides an abstraction of a byte stream to the application, which is at layer 5. Now, it's useful to point out that these TCP connections, when they're established between two sides, are bidirectional. What this means is if I establish a connection with you, I can send you data and you can send me data over this TCP connection. Now, TCP is also responsible for providing reliable delivery and in-order delivery. So that means that TCP is going to handle reordering packets that it receives and waiting to pass them on up to the application until they're in order and can actually be used to reconstruct whatever was being sent. This is as opposed to UDP, which is more message-oriented and basically doesn't provide any of this reliability stuff. If a UDP packet gets dropped, it just gets dropped. UDP doesn't provide any guarantees that this packet is going to make it. It's a very minimal layer over IP. They're both part of L4, but TCP provides reliability, whereas UDP sends its data and hopes that it makes it. So looking at this header, what does the header contain? Well, there's a source and a destination field. And here we have these host port numbers. Now I want to point out there is no IP address here. And why is that? Why is there no IP address in the TCP header? Isn't it needed to know where the packet is going to go? Well, it's because the IP header already contains that destination IP address. Actually, here, if I can put a piece of switch to my iPad here to show this. When we go to send a file, whoops. Say this is from L5, OSCI.png, a photo of our mascot, Berkeley, OSCI the bear. So this is a sequence of 1, 0, 0s, so on and so forth. Maybe a long sequence, maybe a short sequence. But at the application layer, we think about this as an image. Well, at L4, okay, L4 TCP, here in this case, so is going to be responsible for taking this image and breaking it into pieces. And maybe let's say that this OSCI image is 300 bytes. Well, this these pieces that TCP is going to break the image into is, let's say, 100 bytes each. So data, data, data. Now there's going to be a TCP header put on top of this data, this TCP header that we were just looking at, and we'll go back to looking at it in a second. I'll actually make this perhaps a bit smaller. Now at L3, TCP is going to hand off this packet to L3, and L3 here, we have our data, the TCP header, and then the IP header goes on top of that. So it's kind of like an onion. We wrap the data inside of a TCP header at L4, and then wrap that data inside of an IP header. So the IP packet that gets sent, its payload is actually data with a header, with its own header, an L4 header. And later in the semester, we'll also talk about an Ethernet header. It's part of the Ethernet frame that actually puts yet another header kind of on top of our packet. We just haven't gotten to that yet. So L2, let's say we're using Ethernet. We'll actually have something that looks like this. We have the data for this packet, a TCP header, an IP header, and an Ethernet header. So, and this happens for each of these packets. So I really ought to draw more boxes here. to show that each of these packets gets its own header slapped on top. Now, my point in doing all this is to say that when the other end, when the receiver gets this packet, within L3, we're using the IP header to route. So this IP header has an IP destination address. But at the point that you make it to the other side, so if I draw this out here, I say 5, L4, L3, L2, L1. We've seen this kind of diagram where packets go kind of down L1, L2, L3, then up the stack, continuing on 1, 3, up and back down, and finally at the other end, coming all the way back up for L5. Well, with just the IP header, we had no way of distinguishing the application running on the other side. But the TCP header now provides port numbers, host port and destination port, that now tell the receiver which process to actually give this data to on the host, and also tells it which process to send data back to. So this is really useful. Now, these port numbers are 16 bits, and as we just mentioned, they're used for multiplexing and demultiplexing at the sender and then at the receiver. So next we have a sequence number. And this sequence number is going to be the byte offset of the data being sent, specifically of the first payload byte. So what that means is if you're sending bytes 100 through 199 of your data, the sequence number would conceptually be 100. Now, an important caveat is instead of starting counting from 0, we're actually going to start counting from some initial sequence number that our receiver is going to tell us to use. Actually, we will send to our receiver so that they know. And it's going to be initialized randomly. And so because this is a byte stream-oriented protocol, the sequence number is always in terms of bytes, but instead of counting from 0, you count from some initial sequence number. We'll talk about how that's selected in a second. Then the acknowledgement field is set to be an acknowledgement of the sequence numbers received so far. And the way that TCP does this by default is using cumulative ACKs, which means TCP will send back an ACK that represents information about the previous contiguous block of data received. And so if a packet arrives out of order, a future packet arrives and there's still a gap, the ACK is always going to be to inform the sender that everything up until that gap has been received. Okay. Now I'll point out here, the way that ACKs work in TCP are the acknowledgement says the next byte that the receiver is looking for. So what that means is if the receiver has received bytes 100 through 199, the way that TCP ACKs that is it sends an ACK, a packet with an ACK flag that I'll mention in a second, with the ACK field saying 200. That tells the sender that everything up through 199 has been received. And data packets in TCP can carry ACKs as well. We've got the header length field. It's 4 bits in 4-byte words. The TCP header without options is 20 bytes, but it can actually get longer because options are used. Then the flags. There are 4 bits for flags here. There's a SYN, flag, an ACK flag, a fin flag, and a reset flag. And I'll cover these in just a second, what they do. And then we have a advertised window. This is what, in the initial handshake, how the sender tells the other side, one side tells the other side, what rate they can accept packets at. And so this is a way to not waste network resources, where the side that's receiving can tell the side that's sending at what rate it can process these packets. Which then, if the rate that the receiver can process those packets is below the maximum transmission rate on the network, then you send at the lower rate. So you send at the lower of the two, of the sending rate, the network capacity, and the actual processing speed of the receiver. Now finally, and before we get to the data, we have checksum, which I mentioned before is used to verify that none of the data or the header is corrupted, and options. They're actually used in TCP, but we won't talk about them in this class very much.